We'll run through the 4 things that I mentioned in the email. We'll first talk about why using the OLS standard errors in the T-statistic will cause biased inference. So we touched on this briefly in the lecture, and we can just give a bit more detail as to why using the wrong standard errors will cause a problem for inference. Okay, so if we get back to... Okay, so we have here the variance of... Wait, where's the... This here is the variance of this term here when there's no serial correlation. One second, why is it not doing? Okay. One second, sorry. Okay, let's get going. Okay. Okay, so that won't work for some reason, but let's go. So this slide here, we get biased inference. So the question is when we form the T-statistic and we use the OLS standard errors, why do we get biased inference? So namely, why do we get this result here? Okay, well, what we know is that square root t beta hat t minus beta naught tends in distribution to a normal naught sigma squared, normal naught q to the minus 1 lambda q to the minus 1. Okay, which is this here. So this is when we don't make any assumptions on the form of the variance. So for example, if the OLS assumptions hold, we know that the variance simplifies down to this, and we get that q to the minus 1 lambda q minus 1 just equals this should be q there, just equals sigma squared naught q to the minus 1. So this is why we get the simplifications we saw in the first 4 lectures if the OLS assumptions hold. But in general, this is the general variance which doesn't simplify down unless we make these extra assumptions. So the point is we know the limiting variance looks like this. So if we use the wrong standard errors, then of course only in the case where the variance looks like this do we get this result here. So the point here is then this result says that any element of square root hat beta hat t, if we take the ith element, this result holds for every element, all of them. This will tend in distribution to a normal naught. Well, the ith element of this matrix here so what we know is that square root t of beta hat t I divided by this square root of q minus 1 tends inwards distribution to a normal naught 1. Okay, all we've done is divide by this is the variance of this. We just divided by the square root and we get this result. Why is it doing this? Okay. So the point is then, so this result always holds no matter what the form of the heteroscedasticity is. So the problem is that when we form the T-statistic using the wrong standard errors, so if we use the standard errors, if we have well, we've used this estimate here, sigma hat t, the square root of the ith element of this here. So why does this not work? Well, we can just multiply and divide by the actual. So again, so we can see what we're going to see. What we're going to do now is what is the limit distribution of the T-statistic where we use the OLS estimate of the standard errors. Where what we know is this result holds no matter what the form of the heteroscedasticity is. Yeah, this is the limiting variance in the general case, no matter what this omega matrix is. So we're going to look at what happens to the T-statistic with OLS standard errors. Well, we can just multiply and divide. So we can rewrite this as divided by, well, the actual variance, the actual standard error, okay, why is it? Well, and then, so we've got to multiply and divide, right? So we divide, so we times by this. Divided by what we had before. So what's going to happen to both these terms? Well, we're going to use all the results that we've been developing. Okay, is everyone clear how this is the T-stat with OLS standard errors, and we just re-expressed it down here. So we just multiplied and divided by this term here. So what's going to happen to both of these terms? Well, we can derive the limit distribution of this now. Well, we know that this term here has what limit? What's going to happen to this? Using the above result, we know this becomes a normal not 1. So this part tends in distribution to a normal not 1. And what's going to happen to this term that we multiplied by here? Well, we know that sigma hat t will tend in probability to sigma naught, and x dash x over t under the IID assumption and finite will tend in probability to q. So again, so this is by IID and q finite. So again, you've seen all these results before by the Wheat law of large numbers. And again, assuming it's full rank, we get by Slutsky's theorem that this tends toward the inverse of this. And then of course the ith element will also converge to this. So we get the result then that the ith element will of course converge to the ith element of this. So that all together then, using Slutsky, we get sigma hat t times by the ith element of this matrix, of the inverse, sorry. So sorry, this should be the, I've missed out, this should be the inverse of this, sorry. We have the inverse here. Okay. Well, this tends in probability to sigma naught, and then this is by Slutsky's theorem, times by the ith element of this matrix here. So we get the result then. So this term on this term here will converge to, well, it's going to be square root of the ith element of this matrix. So divided by this. I will tend toward, again by Slutsky, will tend toward this. Okay, and this will not equal 1. This here does not equal 1. Well, when will equal 1? It'll equal 1 when delta is sigma squared naught q. In which case the two things will become equal. So we get then that the T-statistic here converges this part to a normal not 1 multiplied by a term which doesn't equal 1, which essentially means it's still going to be normal not 1 but with a different variance, and the constant we multiply by is this. So this term here will equal 1, of course, when the standard errors that we estimate are the same as the actual ones. So again, it makes obvious sense that if we estimate the wrong standard errors, of course we're no longer going to get correct inference. But this is a formal derivation of y. In here, this result. What actually happens is what we've just shown is that this converges to a normal, but will have a variance different to 1, and the variance will depend upon this constant here. And again, we can see, you should be able to see, of course, that these two things are equal. Well, when this holds. When this holds, well, this part here at the top, well, we will get that q minus 1. Again, plug this in from the OLS assumptions, will just equal, well, sigma squared naught q minus 1 I. Sigma squared comes out, and it will just be, which is it. We're going to get, so we take the square root of this, we'll get sigma naught square root of this, so the top will equal the bottom, and we'll get 1. So did everybody follow this? Did everybody follow the broad steps as to why, when we use the T-statistic with the OLS standard errors, why it will converge to a normal distribution where the variance will not be 1 unless these OLS assumptions hold? So does everyone feel comfortable on describing and working through the steps as to showing why we get biased inference here? So again, if you've got any questions, just ask. Hopefully it's still running. Okay, so this is a sketch of why we get biased inference, and what we've shown is it's still the t-stat's still normally distributed, it's just not going to be normal not 1. And we saw this in a simulation. So if you remember the lectures, we gave a simulation to set up some arbitrary regression. We let the error term u be equal to vt, which is some exogenous shock, times by this function of x, which allows then the variance of u to vary with x. And what we showed is that if you look at this, if you derive the distribution of the t-statistic here using the OLS standard errors when there's heteroscedasticity, and again as alpha gets bigger, it means that u varies more with x, so there's going to be more there'll be more change in the variance with x. Well, we saw in the first column here we get that the distribution of the t-statistic, it looks very close to a normal not 1 for various sample sizes. In the next column was alpha equal 1, so there's a slight degree of heteroscedasticity, and again we see it's still normal, it's just that there's a slightly more variation in the actual distribution than a normal not 1. And the final column then, alpha equals 5, there's a strong amount of heteroscedasticity here. We see, for all even big sample sizes, we see that there's a much wider variance than a normal not 1. So it still looks normally distributed here, it's just that the variance is much bigger. So this just means that the actual variance, the t-statistic is still normal, it's just that we got the variance wrong, which is exactly what we've shown here. The t-stat's still normal, it's just that it's multiplied by some constant. In this case, this constant will be greater than 1, because we've seen that the actual variance of the t-statistic with the OLS standard errors is bigger than 1. Okay, so is everyone following this then so far? Is everyone ask any questions? Has anyone got any questions on this so far? So we've just gone through a bit more formally why using t-stat with OLS standard errors will give us biased inference unless the OLS assumptions hold. Okay, so the next result then we said we'd go through was to this one here. So again, we can show this. So there's a small typo in this which I mentioned in the lecture. So what we're going to show is, from slide 21, we're going to show that x dashed u hat u hat dash x. So again in here there's a dash, there's a transpose missing on the second u. We're going to show that this equals the double sum t equal 1 t of u hat s, u hat t, x s, x t dash. So again, and again this u hat t should be this u s times u t. So we're going to show this result, and you've seen something similar to this when he derived the x dash omega x with Alistair. So you've seen something similar to this. So again, it just takes practice. You should be comfortable working with vector matrix type expansions. Well, what's x? Well, remember, so x is a t by k matrix. T is a sample size, and k is a number of regressors. Well, it's just all of the x's stacked. We're going to get x1 dash down to xt dash. Because remember, here, x1 is a k by 1 matrix with all the regressors for time period 1 up to xt, which is again a k by 1 with all of the regressors at time period t. So again, when we transpose this will be, this here's k by 1 by k, this is 1 by k. So when we stack them all together, you can see this is also t by k. So you just verify to yourself that you got it the right way around. And then, well, the transpose, you just swap rows and columns. So the transpose will be x1 to xt. So this is the first column here, becomes the first row here, and so on. So the transpose should be k by t, and again we get that. We get a k by 1 up to a k by 1, and there's t of them. Yeah, so we get a k by t matrix. We then need to work out what's u hat dash. Well, u hat is all of the residuals stacked together. And then obviously u hat dash is then the transpose of this, so it becomes all of them. And again, remember u hat's a scalar here, all of these individuals are scalar. Okay, so then we want to then work out what's u hat dash. So we want to work out what's this here. Well, multiply them together. So just take practice. I'm not the best with matrices. You just have to sit and go through these examples yourself. Okay, so we have a t by 1. Always check everything's conformable by 1 by t, which will give us a t by t matrix, which is what we want. So we just go through. We have, well, each element times together. We're going to get u hat 1 squared, u hat 1, u hat 2, right there up to u hat 1, u hat t. All the diagonals will be squared. And again, this will go down to u hat t, u hat 1. So again, to stop if you've got any questions, it is just kind of somewhat tedious, but you just follow the down to u hat t, u hat 1, and the cross. Okay, so multiply these two together and we get this matrix. And you've seen this kind of matrix before. We saw something very similar when we have the population version of this. We have the E of u, we get all the variances on the diagonal and all the covariances on the off diagonal. So now then, what you want to find out, so this is u hat dash. So we want to find, well, what is x dash u hat dash x? Well, let's put everything together then. Well, x dash from above here is just all the x's, which are all k by 1 vectors together, multiplied by this here. Sorry, that should be. So the u hat t square and so on, just writing out again. Okay, and then, well, what do we have here? We multiplied by x, and remember, take x from here. Just all of them stacked together. Okay, so we've written it out, so now we just need to multiply all through. So the best way to do this is to first start by working out the multiplication for 1. Multiply this by this and work this out first, and then multiply through by this term here. This is the best way to work through this. So here we have u hat 1 squared times x1 plus this times x2, and so on going down. So you can see that we can going to get again. So leave this to be multiplied next. Multiplying this through, and again this is a t by t multiplied by a t by k. So we should get a t by k matrix coming out. Well, we're going to get u hat 1 times this, u hat 1 2, u hat 1 u hat 2 times x2, and so on. So what we can show is that this will be the sum of t equal 1 to t. We're going to get, again, in each one of these as a u hat 1. So we get u hat 1 times by u hat t of xt. So we can see this is what happens here. Each one of these multiplies through. So you're going to get u hat 1 times x1, u hat 1 u2 times x2, right up to u hat 1 u hat t times xt. So each one of them has got the u hat 1 in there. Then we get each one of the t's, we get u1, u2, u2t multiplied by each one of the x1, x2 and xt as we go down. So hopefully you can see that we can write this. This is going to be the sum. We'll multiply this row by this matrix here. We're going to get each one multiplied by each vector. So when we multiply it all out, we get this term here. So just convince yourself that if you rewrite this out from t equal 1 to capital T, we'll get what when we multiply each one through. And we can do this all the way down. And then for capital T, we will get sigma t equal 1 to t, this time for u hat t. And again, the exact same thing. We're going to get u hat t xt. When we multiply this down, so now when we multiply this by this, then u hat t and u hat 2 by this, and down. So again, we get each one of these now, but now multiplied by u hat t as opposed to u hat 1. So it's exactly the same method. So all we've done now, all we've done is work out what this part is here. We just multiplied these two together, and we can rewrite it like this. So again, just convince yourself that when you expand both of these two out, we get what we get above when we multiply each element through and go down. We'll get here, and then just do the exact same thing for the final row here. Multiply them all through, and we'll get this. Okay, and then you do it all again. So now we multiply each one of these through. So, well, we're just going to get x1 times the first element, which is sigma t equal 1 plus, then keep going dot 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 right up to xt times that's capital T there, and then we get u hat little t xt. So this is where the double sum comes from. We can rewrite this in its sum formation. Give it the s equal 1 to t of xs. So this just gives them. This is going to give us a sum of each x1 sum of each x multiplied by well, it's multiplied by this term. So we're going to get the sum t equal 1 to t u hat f u hat t xt, and to see why. So we can see, well, just to double check that these two are equal, well, just write out, expand it. So evaluate this at s equal 1, we're going to get x1 times this, dot dot dot, and at t, well, we'll get xt multiplied by the u hat t and times by this. So if you multiply these two out, you'll see they're both equal to each other. And then that's it. We can just take both the sums outside, and that's why we get the double sum. So it is a little bit laborious, but again, it's the same. Once you understand it for one case, you see this working with what are known as quadratic forms comes up again and again. So we get the result. There's quite a few steps there, but once you understand it for this, you can do it for the population variance and so on. It's always the same steps. You're just expanding out a quadratic. So, are there any questions on that? So, hopefully, again, now this will get saved. It'll be out. This will get saved to the YouTube channel, so you can watch it again, and all the steps will be there. Okay, so we get this result here. So that was just, this was just to get, so again, note the slight typos here, so amend that in your notes here. So we're just showing this result. And again, so why does this equal not? So this was, so the whole point of this slide was, well, just like when we have heteroscedasticity here, we estimate sigma hat t squared by u hat t squared. Well, this is the variance of this term when there's serial correlation. So this is the general variance, and we can see then. So the point was, why can't we just replace sigma st with u hat s u hat t? Very similarly to why we replace sigma t squared with u hat t squared. And the reason it doesn't work is, well, this term, this would be the obvious estimate. To follow this logic, the obvious way would be to replace sigma st with u hat s u hat t. And the reason why we can't use this to estimate this is, well, we've just shown that this equals x dash u hat dash x. And we know for OLS, this by construction equals not. This equals not because x dash u hat equals not. Remember, the OLS coefficient is selected to make the residuals orthogonal to x. So we can't just use this as a replacement for sigma t s x. Okay, so that's why we can't use that. That would be the natural, intuitive way to move from the white estimator, which estimates sigma t squared with u hat t squared. Extending that intuition to the more general case, we can see won't work, which leads us then to the New West standard errors, to come up with a way to estimate this sigma omega matrix when we have serial correlation. So again, this is the New West. So I'm just going to give a little bit more detail where this comes from. So as I made clear in lectures, you don't need to memorize the formula for this. We don't go into any formal proofs of why it works, etc. You just need to understand. You just need to be able to understand that we can't use this here to estimate omega, this variance matrix here. So again, what the point is, we want to estimate this, and we're saying that, well, we can't use this here because we know it equals not. So can we come up with another way of doing it under some assumptions? And the point is, yes, we can. We can use what's known as New West. And just to give you a bit more flavour of why this works, well, we can show that. Here. We can show this. We can rewrite this. We want to estimate this. So we want to estimate, the crucial point is to estimate this omega matrix. Well, the general formula is, we get this double sum here. We can rewrite this. Well, we can rewrite this, we're going to get when s equals t, we get all the variances, so we get sigma. So we get the sum of all the variances, so we're going to get sigma t squared plus the sum of all the covariances. You're going to get the sum where t doesn't equal s of this term here. Yeah. So remember in general, the variance of the sum is a sum of all the variances plus 2 times all the covariances. So let's just get this term here. This is all the covariance terms here, and what we can show is that this term here. So this part we can estimate by the white standard errors. So the white standard errors will estimate this when there's general heteroscedasticity. This is the extra part of the variance which comes in when there's serial correlation. So the New West adds in, relative to white, the difference is it adds in this term here. And this term, turns out, will estimate this under some assumptions, which which you don't need to know, you don't need to go into detail with, but we can show that this additional term here will estimate this under some assumptions. And the reason, what we can show is that t to the minus 1 sigma t doesn't equal s. This term can be re-expressed. So hopefully you'll see a bit more clearly why we can re-express this as t minus 1 2t of e of sigma st plus we can show these two are equal. This here. And to do this, and again you can just take the case for example where t equals 2. You can see that they're both, you do this yourself. When t equals 2, you can show they're both equal. With t equals 3, they're both equal, and so on. So we can re-express this term, this additional term in the variant, which is coming from the serial correlation, in this form here. In this form, there's this form here. So again, this is relatively basic algebra, and just convince yourself for t equal 2, t equal 3, you can show these two terms are equal to each other. So this is why we see this coming in here. You can see that this is related to this. All it's done is replaced basically sigma st with u hat t, u hat s. And again, we get both of this xt term xs here, and we get this term here from here. So this, we get these two terms here, is just estimating both these parts here. And the reason, and remember this WH, so within here, is given beneath. And what this WH do is, the H is the gap between S and T. And what the general rule is that WH will tend to naught as H goes off to infinity. What this means is that this term will give less weight to those points. You give less weight between S and T when there's a big gap between them, and we can see beneath that it sets WH to naught when the gap between them is bigger than some number b, and we can let b grow off to infinity. So all this does is essentially just drops them out. So if the gap between S and T is big enough, it gives naught weight to them. And the reason why this works is that the US standard errors will work well when essentially sigma st x tends to naught as s minus t goes off to infinity. This just says the correlation between US and UT goes to naught as the gap between the two observations becomes bigger. So the further apart we are in time between now and some other point, then the correlation between the residuals in these parts becomes smaller and smaller and smaller. This just means that the population variance, when S is far away from T, these drop out to naught. So it essentially means we can drop these out of our estimate. It means we can drop these out of the estimation. And this is why it works. And again, this is just to give you some more background and intuition to this. Again, you don't need to memorize formulas. You don't need to be able to. You don't need to know the formal assumption. Just to give you a bit of to hopefully see a bit more clearly now that this additional term is an estimate of this part of the population variance here, and the reason it gives lower weight to those observations far away is because we're assuming that these terms here essentially are not for gaps far away into the future. Okay, so hopefully that's just a little bit clearer on why, just a bit of intuition as to why we have this formula for the standard errors when we want to estimate the serial correlations. Okay. So one final thing then, has any questions on this? And hopefully there's any questions so far on what we've been talking about, hopefully. Finally then, we did a simulation at the end. So again, we didn't have much time to go through this properly in the lecture. So, just to recap overall, remember if there's no heteroscedasticity and no serial correlation, then we know we can just use the OLS standard errors. If there's heteroscedasticity but no serial correlation, well, we know that the white standard errors will give us consistent estimation of the standard errors. But again, if there's serial correlation, even white will be biased, because the white standard errors will be inconsistent when there's serial correlation. And finally then, we know that the Newey West will be consistent when there's serial correlation and or heteroscedasticity. So as we keep going down, these more and more general estimates of the standard errors are more likely to be not biased. But again, as we consider more and more general estimators, in essence, for example, when we go from white to Newey West, we're estimating all these additional terms here, which adds in more sampling variation. So the point is, if we knew there was no serial correlation, for example, then we prefer white to Newey West, because white will also be a consistent estimate of the standard errors, but it will also be a much better estimate of the standard errors, because we've not got all the noise coming from all these extra terms. And the same goes for the OLS standard errors. We prefer to, if there was no serial correlation and or heteroscedasticity, then even though the white standard errors and Newey West will both be consistent estimates, they'll be much more noisy, they'll be less efficient estimates of the standard errors, because we've estimated more terms than we need to. So we're going to lose degrees of freedom. So again, for this you just need to understand the intuition that the white and Newey West become much more likely to be robust to bias. However, they suffer a reduction in efficiency, because we're essentially estimating more and more parameters. So we get this bias variance trade-off, which is what the simulation at the end was showing you for a particular example. So again, we set up a regression and we consider 3 different specifications for the residuals. Specification 1 has the errors meeting the Gauss-Markov assumptions. We just set the U to be a normal knot with some constant variance 0.1 squared. The second one just has heteroscedastic errors, so it sets U to be normal, where the variance is either for half the sample is 0.1 and the other half is set to 0.02. So in this case, the variance is not constant across the sample, so we get heteroscedasticity. And the final one then lets the errors be in armor 1-1. This sets the errors to be highly correlated with each other. So what we know, so again, for the autocorrelated errors, we know only Newey West. So for errors for the error 1, so for error specification 1, OLS, white, and Newey West are all consistent, but OLS is more efficient. And again, we're talking about estimates of the standard errors now. So in case 1, where the errors satisfy the Gauss-Markov, all of the 3 estimates of the standard errors are consistent. So a T-statistic based with the standard errors of any of these will be asymptotically valid for T big. But we'd expect OLS to be more efficient, because again, we're estimating fewer terms. For specification 2, both only white and Newey West, both consistent. Remember, Newey West will work when we've got both serial correlation and or heteroscedasticity, and we know white will work. But again, we'd expect white to be more efficient than the Newey West. And finally then, when there's serial correlation, only Newey West consistent. Okay. So we can see then what happens. So what we do is, we set up so the true coefficient on x1 is 1. So we perform a test. We retest the null, that b1 equals 1, against the alternative that it's not. So we know that, so when we do a simulation, we're essentially kind of playing God. We know that the true coefficient is 1. So we've set up a test where the null is true. So we consider sample sizes 20, 50, up to 400, and we set the size of the test to 5%. So what we do is we generate 10,000 samples under these three different error specifications for different sample sizes. For each sample, we work out the T-statistic, and we do that 10,000 times. Then we can plot the distribution of this test statistic. Okay, and we can calculate the size of the test. So remember, the size is the probability that of rejecting the null when it's true. So we expect the size when we do a 5% test, we expect the probability of rejecting the null probability of rejecting the null given it's true to be 5%. So what we do is that we using the simulated data set, we can work out what is the number of times that we reject the null, and we plot this in these three tables here. So again, all these elements are the probability that we reject the null doing a t-test with the standard errors given by here. In the first table, we use the OLS standard errors. In the second table, we use the white standard errors, and in the third one, each table, the first table is GM, is error specification 1, when the error terms satisfy the Gauss Markov. The second one is for error, this is the error specification 2, when there's heteroscedasticity, and the final one is specification 3, when there was zero correlation. And each one of these columns within is the size of the test, the probability of rejecting the null when we use the T-statistic with the different standard errors. And these give you the sample sizes. So for example, this element here, 0.00468, this is the probability of rejecting the null, and again it's true here, probability of rejecting the null given it's true. In the case of error specification 1, where the Gauss Markov held, when we use the T-statistic using OLS standard errors for sample size 20, and we plot this and we give it for sample size 50, 100, 200, 400. So we can see in this case they're all around 5%. I would expect this because we're using this bases inference with the T-statistic using the OLS standard errors, where all the OLS assumptions hold. So it makes sense then that the size of the OLS, the probability that we reject the null, will be around 5%. The next column does the same thing, but now it plots the size of calculates the size of the test on the simulated data when we use a T-statistic with the white standard errors. So for example, this term here gives us 0.1334 is a probability that we reject the null, but b1 equals 1, using a T-statistic with the white standard errors, and we can see this is around 13%. And again, as t gets bigger, as the sample size gets bigger, it eventually becomes 5%. And the same thing for New West. Using New West standard errors, eventually they all become 5%. And this just says again what we know already, that when the OLS assumptions hold, all of these test statistics should have size around 5% as t gets bigger and bigger, because they're all consistent tests. But what we can see is that for small sample sizes, the T-statistic with the OLS standard errors is much more near to 5%. It's got a correct size. We're not getting biased inference. And this just gives you an example of what I was saying, that although the white and New West will both be consistent tests, in small samples they can be very noisy estimates of the standard error. So we'd expect to get the size of the test wrong. And we can see that it's quite drastic here, that for sample size 20 and 50, the size of the test is much bigger than its sub B. So for example, we've set the test to reject 5% of the times when the null is true, but for example, for sample size 20 for the white standard errors, it's more like 13% and 15% for New West. So that means we're going to over-reject. Okay? And we can work through. So in the next case, we did error specification 2, when there is heteroscedasticity. So again, OLS will be biased here. So again, even at t equals 400, the size is around 6% when it should be 5. We know in this case both white and New West will be consistent. So as t gets bigger, it should get near 5%, which is what happened. But we can see in small sample sizes, the probability of rejecting the null given it's true here, is huge, much bigger than 5%. So even in the OLS here, is much, for smaller sample sizes, actually much smaller or very similar to the size of the white or the new US standard errors. So we can see that OLS is actually, it's actually better, or the white and new US are only slightly better. These are only slightly nearer to 5% than OLS for T equal 400. We can see the downside is that smaller sample sizes, 20, 50, 100, 20 and 50 say, the size of the test of the OLS is much nearer to what it should be, 5%, than is white and new US. This just gets to the point that the OLS standard errors, even if they're possibly going to be biased, can still be much better estimates of the standard errors in small samples than these consistent estimates. And finally then, the final table gives you the size of the test in error specification 3. And again, we can see in small sample sizes, even though the OLS standard errors are incorrect, they're still much nearer, the size is much nearer to 5% than is those based on white and new West. Okay? So the final simulation just shows what we motivated here, that there's this bias variance trade-off. Even the OLS estimates of the standard errors will be incorrect when there's heteroscedasticity or serial correlation. They can still actually be, in small samples, much better estimators, be much more efficient and be nearer to the true standard errors than these robust estimates which we've been given here.